Now, it's relatively straightforward to find R2 and R3 if we just assume a voltage, yeah. I only gave you the magnitudes of these voltages, okay? I didn't give them to you with the signs and so forth, so you're kind of free to choose your signs, right? Okay, but I'm going to assume that you have a voltage drop across here when you go in this direction and a voltage drop across here. Okay, so assume and this is of course voltage drops. I just said drops, I should have said voltage drops. Okay. And that's in the clockwise direction. Now if you assume then that you have a 3-volt drop from here to here and a 3-volt drop from here to here, well, you know that everything that's directly connected to this terminal of the source, and you know, I'm going to change this, okay, because I want the voltage to go from positive here to negative around here, right? Well, no, that would be that would be a drop. Never mind, that's in the counterclockwise. That's in the clockwise direction. Okay. Okay. So it's like, you know, this will be positive at this moment, this will be negative. Now that could change depending on what this thing's doing, right? Could be an alternating current or something. And then we're going to have positive here and negative here. Okay? No, sorry, we have positive here and negative here because we're dropping in this direction. You've got to be careful about that. Unlike some people I could mention in front of the camera. Okay? Well, in this case, you know that between here and here, you have the same voltage you have across the source, right? So you have a 6-volt drop between here and here. Okay? But 3 volts of that's across the capacitor, right? Okay? So that means R3 has a 3-volt drop, whereas R2 has a 6-volt drop. Okay? Then okay, let's do that. You got 6 volts between here and here, right? A 6-volt drop, and let's say 6-volt drop in this direction. And you have a 3-volt drop from here to here, which means you got a 3-volt drop from here to here, right? So I3, guess what? It's 3 volts over R3, which would be 0.3 amps. Now, when you all worked it out, I guess you both got 0.9 amps because you assumed the capacitance, you assumed the drop was in this direction across here, which means you'd had to have 9 volts across R3.
Right.
So it's perfectly all right.
Okay.
Okay?
Okay.
Because I told you that you know, I didn't give you signs on these things.
Right.
I just gave you magnitudes.
Right. Okay.
So you made an assumption that's different than mine. Mine is much simpler. No, it's pretty simple either way. okay? And you had no trouble getting the right result for your assumption, okay? Well, anyhow, in that case, well, current across R2 doesn't care what is happening across the capacitor. Now, if I had a resistor in here, that would have an effect, and we'll see that in a minute. But since we have R2 is 10 ohms, you got 6 volts through this, so you got 0.6 of an amp here.
Right.
Okay? So that's 0.6 amp. Okay, so those two are easy to get. And then I1, because I asked you for I1. So you just look here, you got 0.3 of an amp here, 0.6 of an amp here, so I1's got to be 0.9 of an amp, right? Now you could write out the node equation here, but it's unnecessary in this simple case. Although if you find it necessary, that's fine. Okay, so I1 is 0.9 of an amp. Okay?
Right.
Now the question is, what's the change in the voltage across your capacitor in a time interval delta t? So go ahead and figure that out. You can figure it out for your own solution.